Hi folks, welcome back to 11.1 sequences and their notation, and we're going to take a look at in part 3 at a few more examples where we're learning how to graph a little bit as well. So example 4, consider the formula a sub n equals negative 3n plus 9, where n is greater than or equal to 0. So same first question, is the formula recursive or explicit, and how do you know? Okay. And so one of the things I notice here is that in my equation, I only have n's. I don't have any a sub n's. I just have n, right? So in that case, we can say that the formula is explicit since we only need to know right? Since we only need to know the value of n to find the nth term. Okay. Meaning, if I wanted to find that 1000th term, all I have to do is plug 1000 in for n. I don't need to know what the 999th term is. I can literally just plug in 1000 for n. Okay, so this is an explicit formula. We're going to determine the first 5 terms of the sequence, and then we're going to plot the terms on the grid. Okay, so we might notice here that this says n is greater than 0, greater than or equal to 0. What that means is that our first term here is actually a sub 0. Okay, so if it tells us n is starting at 0, we have to start with a sub 0. Okay, and that just means we grab our equation and we plug in 0 everywhere we see an n, right? So that means I'm going to have negative 3 times 0 plus 9. So negative 3 times 0 plus 9 will give us 9. Okay, that gives us our a sub 0. All right, our a sub 1, negative 3 times 1 plus 9 is going to give me 6. A sub 2 is going to be negative 3 times 2 plus 9, which gives us 3. Okay, and so we might be noticing that this number is the same as that. So the 0th term, we plug in 0. The first term, we plug in 1. The second term, we plug in 2. That's how this works, okay? Now we got to find the first 5 terms, so I need a sub 3 and a sub 4. This will give me 1, 2, 3, 4, 5 terms altogether. All right, negative 3 times 3 plus 9 is 0. And finally, negative 3 times 4 plus 9 is negative 3. Okay, so let's go ahead and plot these points. So 0, 9, 1, 6, 2, 3, 3, 0, and 4, negative 3. All right, those are our coordinates. I'm going to do them in blue just so we can see them a little bit better. But our first point is at 0, 9. Our next point is at 1, 6, and then 2, 3, and 3, 0, and then 4, negative 3. Now this might look suspiciously like some things we talked about at the very beginning of the summer, right? We looked at mapping diagrams and tables and we plotted things. But one thing I do not want us to do is connect them. And I know that's probably weird for us, right? This is the first time that someone has said, don't connect the point. One of the things that's important to know about sequences is that they are discrete functions, meaning we have a value for 0 and for 1 and 2 and 3 and 4, but we don't have a value for like 0.5 or like 1.1 or 2.8. It's only whole number values, integer values. So if you connect all of them, then what you're telling me is you don't really understand what a sequence is. Okay, so to show me that you understand it's a sequence, we leave our dots, we do not connect them, and that's fine. Okay, so let's leave that note for ourselves. Do not connect points. The reason being this is discrete function. Okay, all right. Got one last question here. If the formula is recursive, write the corresponding explicit formula. However, if the formula is explicit, write the corresponding recursive formula. So we said earlier that the formula is explicit. So now we need to write a corresponding recursive formula, meaning I want to write a formula where it tells me what to do based on the previous point. Okay, so in writing these, let's see if we can find a pattern here, right? Every time I go from one value of n to the next value of n, what's happening to the output values? Well, 9 to 6 to 3 to 0 to -3, it sure looks like I'm subtracting 3 every time, right? And in fact, if we were to connect these points, which we're not going to, but if we were to imagine that line going through there, we would see that it has a slope of -3. Okay. So what I want us to do here is practice writing this recursive formula. We always have to give our audience a starting value. So you can't just say subtract 3 every time. You have to say a sub 0 equals 9. This is where you start counting from. Then you say to find any term. So a sub n is going to be the previous term, a sub n minus 1 minus 3. And we want to tell our audience that this is true for all n greater than or equal to 1. We don't include 0 because we already started with that 0th term. That first term was our 0th term. So then after that, we plug in 1, 2, 3, 4 for our n values. Okay. Now, a few things here. When we have a number like this -3, where we're just subtracting the same number all the time, or if we are adding the same number all of the time, we call this a common difference. Okay, so we call this a common difference. If we are adding or subtracting the same number, common difference. Okay, and this also corresponds to the slope of our function. Okay, now if we went back and looked at our initial formula, this kind of looks like a y equals mx plus b situation, right? Our m is 3, our b is 9, or our y-intercept is 9, and our slope is -3, right? So it turns out this slope is exactly what we call a common difference in our recursive formula. Okay. All right. So that's what we have for example 4. Let's go ahead and try example 5 now. So consider the formula a sub n equals 2 to the n, where n is greater than or equal to 0. Is this formula recursive or explicit, and how do you know? I hope that we see again, there's only n's on that one side. So to save us a little bit of time, I'm going to go ahead and copy what I had written up here. And we're going to plop it right in this box. This formula is explicit for the same reason. We only need to know the value of n to find the nth term. meaning this is a formula where if I wanted to find the 1000th term, just put 1000 in for n, done and done. Okay. All right. Determine the first 4 terms of the sequence, and then we're going to plot the terms on the grid. So let's get started. A sub 0 equals 2 to the 0, which is 1. A sub 1 is 2 to the 1, which is 2. A sub 2 is 2 squared, which is 4. And the 4th term is 2 to the 3rd, which is 8. Now, again, the 0th term, we plug in 0 for n. The first term, we plug in 1 for n. The second term, 2, 3, and 3. Okay, so the pairs that we're going to plot are 0, 1, 1, 2, 2, 4, and 3, 8. Let's do that in the blue again, just to make it a little easier to see. 0, 1, all right? And we've got 1, 2, 2, 4, and 3, 8, okay? Now, I am not going to connect these, right? Because again, this is a discrete function. We do not connect them. But if we were to find the a sub 4, that would be up here at 16. And that might be a little easier for us to see that we actually have which parent function? That's right. We have an exponential parent function here. Okay. All right. Now, part D, if the formula is recursive, write the corresponding explicit formula. However, if the formula is explicit, write the corresponding recursive formula. So let's see what's happening in our terms here. We start with 1, and then we multiply by 2, we multiply by 2, we multiply by 2. So every time we're finding the next term, we multiply by 2. Well, to write a recursive formula, then, we have to tell our audience that we are starting at 1. That is our first term. And then to find any other term, we do 2 times the 1 that came before. And this is only true for n greater than or equal to 1. Okay? So this, my friends, this times 2. So now we are not adding 2 or subtracting 2, but times 2. This is called a common ratio. Okay? And a common ratio implies that we will have an exponential shape. All right? If I have a common ratio of 2, that means I'm multiplying by 2 every time. If I had a common ratio of 11, that would mean I'm multiplying by 11 every time. And if I had a common ratio of like 2/3, that would mean that I'm multiplying by 2/3 every single time. Okay. So let's get this all on one page over here. But we've taken a look at 2 examples where now we have these explicit formulas. How do we recognize them? How do we use them? How do we graph with them? All right. And in our last video, we're going to take a look at some slightly different examples just to show that this world of sequences can be really so broad for us. Okay. So I'll see you back here.